Let's look at the procedure for computing the present value of an ordinary annuity using semi-annual compounding. Suppose we want to compute the present value of an annuity that pays $1,000 per year in semi-annual installments over 5 years using an annual interest rate of 12% compounded semi-annually. To solve this problem, we enter n as 10 because we have 5 years of 2 compounding periods per year. So n is 10 compounding periods. We enter I over y, or the interest rate per compounding period, as 6, because we have a 12% annual rate in 2 compounding periods per year, or 6% per compounding period. We enter payments equals negative $500 because we have a $1,000 annual payment that we receive in semi-annual installments. We compute the present value of $3,680.04. Let's look at another example before we move on. Assume we want to determine the rate of return that we will earn on an ordinary annuity that requires a $700 deposit today and promises to pay $100 per year for each of the next 10 years. We can determine the discount rate or rate of return on this annuity by entering n equals 10, PV equals negative 700, payment equals 100, and compute I over y to get a result of 7.07%. Note here that the payment and the present value were input with opposite signs. We had a negative input for the present value and a positive input for the payment. This opposite sign convention is necessary whenever computing the interest rate or the number of compounding periods in order to avoid obtaining an error message. Next, let's calculate the present value of a perpetuity. A perpetuity is a financial instrument that pays a fixed amount of money at set intervals over an infinite period of time. Essentially, a perpetuity is a perpetual annuity. British bonds, called consols, and most preferred stocks are examples of perpetuities. They make fixed interest or dividend payments forever. We can compute the present value of a perpetuity by simply dividing the periodic payment by the periodic interest rate. Let's look at an example. Assume that a corporation pays a $4.50 per year dividend and plans to follow this dividend policy forever. Given an 8% required rate of return, we can compute the value of this corporation's preferred stock by dividing the dividend by 8%, or $4.50, divided by 0.08. The result is $56.25. This means that if an investor requires an 8% rate of return, she would be willing to pay $56.25 for each share. Let's look at an example where we want to determine the rate of return for a perpetuity. Here again, we will use a preferred stock. Suppose we want to determine the rate of return that an investor would realize if he paid $75 per share that paid a $4.50 dividend. By rearranging the present value formula, we can express the rate of return as the payment divided by the price, or the payment divided by the present value of the perpetuity, which in equilibrium will be the price. So for our example, we divide the $4.50 dividend by $75, and this gives us 6%. The return on a $75 preferred stock that pays a $4.50 annual dividend is 6%. To determine the present value of a series of uneven cash flows, we can simply take the present value of each of the individual cash flows, discounted over the relevant number of periods, and sum these individual present values. It is also possible to compute the present value of an uneven cash flow stream by using the cash flow or CF keys and the net present value, the NPV function, on your calculator. The procedure for computing the present value of an uneven stream of cash flows is described in Schweizer's downloadable calculator tutorials, Book 1 of the study notes, and in your calculator manual. However, on the exam, it is most likely that you will be given just a few cash flows in an uneven cash flow stream, and you will most likely find it easier to simply sum the present value of the individual cash flows to determine the present value of an uneven cash flow stream. The cash flow additivity principle states just that. The present value of any series of cash flows is equal to the sum of the present values of each cash flow. The same principle holds for the future value of any series of cash flows or groups of cash flows. Our next learning objective is to demonstrate the use of a timeline in modeling and solving time value of money problems. Most of the present value problems that we have discussed so far involved cash flows that were discounted back to the present. In this case, the present value is said to be indexed to t equals 0. For example, the present value of a 3-year ordinary annuity that is indexed to t equals 0 is computed at the beginning of year 1, which is t equals 0. Contrast this situation with another 3-year ordinary annuity that doesn't start until year 4 and extends to year 6. It would not be uncommon to want to know the present value of this annuity at the beginning of year 4, in which case the present value is indexed to t equals 3, because the beginning of year 4 is the end of year 3. Now that we have become proficient with the application of time value of money concepts, we can calculate the required payments on a bank loan. Assume that a company wants to borrow $50,000 for 5 years. Further assume that the company's bank will lend the money at an annual rate of 9% compounded quarterly and requires the loan to be paid off in quarterly installments. We can compute the amount of these quarterly installment payments by entering the following inputs. For n, we enter 20, because we have 5 years with 4 compounding periods per year for a total of 20 compounding periods. The interest rate per compounding period is 9 divided by 4, or 2.25. The present value is negative $50,000, and we compute the payment to be $3,132.10. Let's take a look at one last example. Assume that a 35-year-old investor wants to retire in 25 years at the age of 60. She expects to earn 12.5% on her investments prior to her retirement and 10% thereafter. How much must be deposited at the end of each year for the next 25 years in order for her to be able to withdraw $25,000 per year at the beginning of each year for the 30 years from age 60 to age 90? This type of problem must be solved in 2 steps. First, we must determine the nest egg amount that must be on deposit in the retirement account at the end of 25 years in order to fund the 30-year $25,000 annuity due. Second, we need to compute the annuity payments that must be made to achieve the nest egg requirement. In other words, we need to find the size of the desired nest egg to satisfy the retirement spending pattern, and then find the size of the annual deposits that need to be made in order to accumulate the required nest egg. The required nest egg in this example is the present value of the $25,000 30-year annuity due at the beginning of year 26, or the end of year 25. This amount can be determined by entering the relevant data with the calculator in the end mode and computing the present value. In this case, we enter n as 29, the interest rate is 10, the payment as negative $25,000, and we compute the present value of $234,240. Now, we must add the first annuity payment, and in this case we get $234,240 plus $25,000, or $259,240. This is the size of the nest egg that must be on deposit at the end of 25 years. Given the required nest egg, we can calculate the annual payments that must be made into the investment account in order to accumulate the nest egg amount at the end of 25 years. To do this, we enter n equals 25, an interest rate equal to 12.5%. Future value is the nest egg amount of negative $259,240, and we compute the payment to be $1,800.02. So this means that the investor must deposit about $1,800 per year at the end of each of the next 25 years in order to accumulate a nest egg of $259,240. With this nest egg, our retiree will be able to withdraw $25,000 at the beginning of each of the 30 years following retirement.